analysis, and then start the new set of notes, which is going to start with composite cross-sections, and then we'll roll into things like skewed cross-sections or asymmetric cross-sections and skewed loading. So again, remember next Monday I won't be here, so we won't be meeting. There will be a recording instead. I still haven't quite figured out which lecture that's going to be, but I'll let you know when I do. And homework 4 and 5, is that right, those numbers? Yeah, homework 4 and 5 both due next Friday. So both focused only on finite element analysis. Originally I was thinking homework 5 might incorporate some of the new stuff from the new notes that we'll start this week, but as I was looking at the schedule, it makes sense to just kind of push that out to the next one. So yeah, any questions? Okay. Alrighty. So we left off last time, wrapping up the discussion on this example, which was a 2-element frame. So we just kind of talked through that process and then briefly touched on the results there, right? So again, I didn't spell it out in this example, but I would like to see you in your work write out the full sum of moments check to verify that sum of moments is equal to 0. No, statics exam? Yeah. All right. So on the next page, we just have this is the same example that we just looked at, but demonstrating how I would organize it in an Excel spreadsheet. So when you have the larger problems, it gets cumbersome to do all this stuff in your calculator. So I highly recommend using Excel. If you're more comfortable with MATLAB or another program, you're welcome to do that as well. I won't be asking you to submit your electronic solutions. Just write down the relevant matrices in your hand calcs and submit it, but feel free to do all the math separately, right? The one thing, if you do want to do Excel, remember that the trick to matrix math in Excel is to type Control Shift and Enter after the command, right? When you do the mmult or minverse in Excel, you type that command in and then you hit Control Shift and Enter. So yeah, that's the trick. I can post a brief video that goes over that, or a link to the video anyway. It's not my video, but it's a good short one on YouTube. All right, so the next example, we'll just talk through this one very briefly because it's not that interesting. It's the same setup as before, except now we have pinned supports instead of fixed supports. So what this does is it adds to our unknown displacements, right? So now we have, instead of knowing the rotations at nodes 1 and 2 to be 0, we don't know what those are, right? So our first partition then will be associated with the rows that have known forces. And in this case, now we know that the moment at nodes 1 and 2 is equal to 0 because there's no fixed support there. So it's not a reaction, and there's no applied moment there. So we know that it's equal to 0. And then the columns that we would eliminate would be just the 4 that are associated with the transverse or translation in X and Y at nodes 1 and 2, right? So that would be column 3, or columns 1 and 2, rather, and then columns 4 and 5. So that would leave these as our first partition. All right, so we would piece that together to get a 5 by 5 for our first partition, solve that for the unknown displacements in terms of the applied load P, and then use that result to obtain our second partition I guess, yeah, so this example just shows the first part of the solution, right? Solving the first partition. But if you wanted to complete the problem, you would use that result, plug it back into the overall matrix, but only worry about the remaining rows that are associated with the reactions, and then solve for those reactions. Any questions there? All right, the next example is a little bit more interesting. So here we are going back to fixed supports at nodes 1 and 2, but now we have a pinned joint between the beam and column. So before we were dealing with rigid joint, right? But now with a pinned joint, that creates some additional degrees of freedom that we need to consider, or yeah, technically, right? So essentially what it means is we can no longer say that the rotation at the end of the beam will be the same as the rotation at the end of the column, all right? So we have to kind of break up the moments and rotations at the end of those members at node 3. And so that means we're going to add a column and a row to our matrix. So here we're separating this into theta 3, 1 times L, and theta 3 associated with member 2 times L. All right, and then, so that's that down there, and then we have, again, the moments at node 3 associated with element 1 and then separate for element 2. So then our first partition will consist of the last 4 rows in this matrix. And so we'll use that to solve for the unknown displacements at node 3. And so as you can see in the result, for this particular configuration and loading, what it means is the beam will not rotate at its end, but the column will rotate, experience rotation, right? So that's essentially going to look something like this if we were to sketch the deflected shape. The horizontal displacement at node 3 is in the negative direction, so that makes sense, right? No vertical displacement. So that node is going to move somewhere over there, and then that column will bend to meet that position. All right, so at that location, that would be your theta 3. And as a gut check, right, that would be a counterclockwise rotation, which is consistent with the positive result we got from the finite element solution. All right, questions on finite element analysis in general? All right. I'll give folks a moment to finish writing, and we'll switch over to the next set of notes. And if you missed it, the announcement earlier, in case you don't have the fresh set of notes today, that's probably okay, because all you're going to be missing out on are the pre-drawn figures. So you can add those in later or whatever you want to do. All right. All right, so now we'll talk about composite beam bending analysis. And this is a topic that I expect you have all seen at least some exposure to in mechanics of materials. We're going to demonstrate a different approach to solving these problems most likely. I guess it depends on who taught it, but the way that I have taught mechanics of materials, the composite topic on that, in that course, is a little bit different than what you're gonna see today. I think that the approach demonstrated in this class is easier to implement, to be honest, and it's also more accommodating. So if you have more than 2 materials, it's really easy to incorporate that. Whereas I think the approach in mechanics of materials, you probably transformed the geometric section according to a ratio, right, a modular ratio based on Young's modulus. So you can certainly apply that to multiple material, like more than 2 materials, but it can get a little bit cumbersome and complicated, and you have to calculate the moment of inertia multiple times. So this method is, I think, a lot cleaner and easier to apply. So at least, at the very least, after this, you will know more than one approach. So you can pick your favorite. I wouldn't recommend going with the other approach in this class, just because of the types of problems that we're going to look at, but I would accept it as a valid solution. All right, so basic intro, right? If you have a beam that has 2 or more materials in it, then as long as the cross-section is symmetric about the vertical or the transverse axis, and if the materials are sufficiently bonded to each other so that plane sections remain plane, then everything that we do in this lecture will apply. So I'm going to write out all those assumptions first. So I'll do a quick sketch, right, to emphasize the importance of that second point, that the materials are sufficiently bonded together so that plane sections remain plane. If we have an unbent composite section like this, all right, and we just divide it up into segments. After applying a moment to that, right, it will bend. All right, something like that. And those lines that were originally perpendicular will remain perpendicular to the longitudinal planes, right? That's what we want to see. What we don't want to see is independent bending, which would look something like this. right? So we don't want that. All right, so now on this image here, we have generic A1, A2, so different areas representing different materials, right? And I'm going to go ahead and note on here the distance measured from the bottom of the cross-section to the centroid of each area. So we'll call Y1 bar to that A1 cross-section centroid, and then Y2 bar for the A2 centroid. So the first step is to locate the neutral axis. All right, and here's a familiar image showing a finite length along the longitudinal direction, dx, under positive bending. All right, so here's that cross-section, or the beam depth is shown here, right? We can see the A1 hatched in red and the A2 hatched in blue. I heard about this, yeah. I'll just wait a sec. I don't think you have to do anything. It's just a test, right? Yeah. Oh, okay. Message received. All right. I think we're in the clear. All right. So back to this image, right? So we have we just have this finite length dx under bending. So we've seen versions of that sketch before. Here, right, the view would be in the XY plane, right, with X along the axis. Now, in this sketch, the neutral axis is arbitrarily placed within the second area. It could be anywhere within that cross-section, though. So it could be an A1. We're trying to find that location, right? So a few things to define first. From this image, Y bar is representing the location of the neutral axis measured from the bottom, assuming positive curvature. Rho is the variable radius of curvature measured to, or not variable, I should say, it's the radius of curvature measured to the neutral axis. And then at the neutral axis, right, there is not going to be any change in length due to beam bending. So we know that is a characteristic, a defining characteristic of the neutral axis. So using that, we can relate the strain along the depth of the cross-section, the longitudinal strain specifically. So the longitudinal strain, which is in the x direction, will be equal to the variable distance y minus y bar times d theta divided by the original length dx, or negative 1 over rho times y minus y bar. And we derived some of these relationships previously in the general beam bending lecture a few weeks ago. All right, so this y is the variable distance to the neutral axis, measured from the bottom for now. Let's see. No, I mixed that up. So y is variable distance measured from the neutral axis to the point where we're evaluating strain. All right, I apologize. I am jumping ahead. So y, that's normally what y is for us. At this point in our derivation, the variable distance y, we're still measuring everything from the bottom, right? So variable distance to the point where strain is calced. And I'll say from bottom.
So if you were to like be designing a composite beam of some sort,
Mhm.
would it be best to try and put the line where they're meet at the neutral axis so that you don't have like strain going on there?
Not necessarily, no.
Okay.
I mean, if a goal was to not have any strain or normal stress at that interface, then you certainly could, but usually the bond is stronger than the materials because you don't want that bond to fail, right?
Right.
So yeah, so it's not really that important to do that.
Not typically an issue with it.
Yeah, there shouldn't be. I mean, if you suspect that there could be, then yeah, maybe you want to try and make that closer to the neutral axis, but I don't see it driving any design decisions. Yeah, yeah, good question. All right, so since we also have our stress-strain relationship tied to material properties, all right, and in this case we have two material properties. So we need the normal stress in X. Using our fundamental mechanics concept that with pure beam bending, there will be no net axial force, right? Since with pure beam bending, you have a resultant from the tensile normal stress should be equal to the magnitude of the resultant of the compressive normal stress, right? I reversed those arrows, but I guess it depends on your frame of reference there. So we're going to use that to complete our derivation of locating the neutral axis. So we will say fx, which we know is equal to 0, is also equal to the integral of the normal stress as it's distributed over the area. And then making our substitution for normal stress in terms of strain and Young's modulus, and then from above for strain in terms of rho and the variable y and the neutral axis position, we get -1 over rho times the integral over area A1 of Young's modulus E1 times variable y minus y bar dA1 minus 1 over rho times the integral over area A2 of E2 times y minus y bar over area A2. And set that whole thing equal to 0. Since y bar is going to be a constant, right, because it's just defining the location of the neutral axis, we can pull that out of the integrals. So we have capital E1 y bar A1 plus capital E2 y bar A2 minus E1 times the integral over area A1 times y dA1 minus capital E2 times the integral over area A2 of y dA2 is equal to 0. And I just dropped the 1 over rho out of this expression because we know rho is not going to be equal to 0, right? So we're just sticking with this portion from this point on. So just so you know, that was intentional. All right. Now looking at these last two terms, the integral over an area of y is equal to y bar 1 times A1. And similar for area 2. So we can then solve for y bar, and we end up with a fraction where the numerator has capital E1 A1 y1 bar plus capital E2 A2 y2 bar. And then in the denominator, we have capital E1 A1 plus capital E2 A2. All right, so that is perfect for cross-sections that have two materials. If you have more than two materials, the general expression is y bar is equal to the summation of each individual capital E, capital A, capital E, capital A, y bar divided by the summation of capital E, capital A product. And now that we know the location of y bar, we will place the x-axis at the neutral axis. So that's what's shown below. Now that the neutral axis is located, we can measure any variable y to area 1 All right, so if we want to know any point within E1, say, since I have the colors cued, I'll color code them. All right, so that would be a variable distance to some arbitrary point within area 1. And then for area 2, since, right, assuming the neutral axis lands in area 2, that variable distance y for area 2 could be positive or negative. All right, depending on what point you're evaluating. So I'll note down here that y1 and y2 are measured from the neutral axis to the location of interest within those areas. And emphasize that y1 and y2 are variable. So if we wanted to calculate the normal stress in area 1 at an arbitrary point, then we could use capital E1 times strain 1, or negative capital E1 over rho times y1, right? And similar for normal stress in area 2. So we still need to derive the rest of the relationship, which would relate those stresses directly to the moments, or the applied moment M, right? So we want to define the corresponding moment in terms of what we've already established. So M would be equal to negative integral over area A1 times normal stress in 1 times Y1 minus the integral over area 2 times the normal stress in area 2, or at that specific point at least, in Y2. So then making first this substitution, we will get E1 over rho in front of the integral of y1 squared dA1 plus E2 over rho times the integral of y2 squared dA2. And we already know that the integral term corresponds to moment of inertia. All right. So you still have to calculate moment of inertia for these problems, but you don't have to transform them, which is nice. All right, so since we have those moment of inertia definitions in there, we can rewrite the moment expression as 1 over rho times, in parentheses, capital E1, capital I1, plus capital E2, capital I2. And then if we substitute 1 over rho we get negative sigma x1 over capital E1 y1. Or what am I saying? All right, we're substituting this term for 1 over rho, and we're also substituting the equivalent for area 2. All right, so plugging those substitutions in, now we get our expressions for normal stress in material 1 at a given location y1. So that would be negative capital E1 times the moment times the variable distance y1 divided by E1 I1 plus E2 I2. And similar for the normal stress at a given location within area A2.
You have the first M doesn't have a subscript, and the second one does.
Oh, good catch. Yeah, thank you. There should not be a subscript on the M. All right, questions so far?
The inertia will deal with the densities of these two,
No, so that it's not the mass moment of inertia, it's just the geometric.
just.
The moment, the area moment of inertia, cross-sectional area, yeah.
And that y is still measured from the bottom of our beam? Y1 and Y2?
No, these are now measured from the neutral axis, yeah,
Okay.
yeah,
Gotcha.
yeah. Yeah, initially we had to put them at the bottom
Right.
to get to that, to figure out where the neutral axis is located, or define that location anyway. But now that we know where they are, we measure from the neutral axis.
So then Y2 goes in as a negative value?
It depends on where within.
Oh, sure. right.
Yeah, if
Okay,
if
but
it's below the
down.
neutral axis, then yeah, it would be a negative value.
Okay,
yeah.
makes sense.
Yeah, so a few more comments then. Since dx, which was the original length of that finite length along the beam, this image right here, right? That would be the length of the neutral axis, also the undeformed length of that finite segment. That's equal to rho times d theta. Or if we write in terms of 1 over rho, we can say that's equal to d theta divided by dx, which we can relate directly to the transverse displacements or deflections, right? So d theta dx is the same as the second derivative of the deflection, right, with respect to x. So this would be the equation to integrate for beam deflection. Now, an example consistent with what we've been focusing on in our derivation shows the strain distribution and the stress distribution along the depth of that cross-section. And as you can see, the strain distribution is linear throughout the depth, so the strain does not depend on material. The stress, however, does depend on material, right? So you see a jump, a sharp change at the interface. And so that will always be the case for composite sections. Strain and stress, or I should say, I think I misspoke. I said stress is not linear. It is linear, right? Both are linear. The stress is not continuous. That's the difference. Yeah.
That's because of the assumption we're making in the beginning that strain is just continuous because everything has to be conforming.
Yeah, so the plane sections remain plane.
Yeah.
Yeah. Yeah, so that's why we can say that the strain is linear and continuous. Yeah, we can say that it's continuous because of that assumption that plane sections remain plane. Exactly. And then, of course, the discontinuity in stress comes from this relationship right here, where you have different material properties, right? Yeah.
That wouldn't, I guess the plane sections wouldn't necessarily remain plane over the whole depth at a certain depth of beam, right? Like you could get like a deep enough beam where like it doesn't necessarily have a linear distribution.
Sure, yeah. So if you have a really, really deep beam, then it's a different approach to kind of tackling the shear and moment. It's more of a Timoshenko type. I don't know if you've heard that in other classes, but it's usually not something that's covered much in undergraduate courses. But yeah, it would be kind of a different approach to sorting all that out. But it would be hard, I imagine, to, yeah, because if you, in that situation, I imagine you would just have more of a shear dominant behavior than a bending dominant behavior. So yeah, we're focused on bending dominant behavior here, where we can generally assume that plane sections will remain plane. Yep. Yeah, good question. All right, so where are we? About 6 minutes left. So we can go ahead and start this example. It's pretty simple and straightforward. So here we have a rectangular cross-section, 2 materials, interface midway through the depth. We're given the material properties, and we're also given the allowable stresses for each material. So we're trying to find the maximum moment that is allowed on this cross-section. So first of all, we need to locate that neutral axis, right? So we'll just recognize that the 2 cross-sectional areas are the same. So we'll simplify our notations with just calling them both A. And then to locate that neutral axis, we'll have A times EA times Y bar A plus A times EB times Y bar B divided by area times EA plus EB. And we can only make that simplification, right, because they have the same cross-sectional area. Here, all the A's cancel out. So plugging in numbers, we have 168 for material A times the distance from the bottom to the centroid of A, which would be 3 plus 1.5, so 4.5, plus 90 for material B times 1.5, divided by the sum of the 2 material properties, which is 258. And so this calcs to be 3.45 units. Will be consistent with what was given, so millimeters. Moment of inertia for each one. We'll have our formula BH cubed over 12 plus AD squared. So we have to apply the parallel axis theorem for both because their centroids are not the same as the centroid of the composite. So for material A, D will be equal to y bar A minus y bar. So that'll be 10 for the width times 3 cubed over 12 plus 30 times 4.5 minus 3.45 quantity squared, which gives us 55.6 millimeters to the fourth. And then similar for IB, we'll have 10 times 3 cubed over 12 plus 30 times 1.5 minus 3.45 quantity squared. So 137 millimeters to the fourth. And then we just go to our equation for stresses and plug the values in. So normal stress in material A. Now what we're after, right, we're given the allowable stresses. So we're actually solving for moment here. All right, so we're gonna set the normal stress in material A equal to the allowable, which is given as 120 megapascals. Set that equal to capital EA times M times YA over capital EA IA plus capital EB IB. So that's going to be 168 times 6 minus 3.45 times the moment divided by the denominator here comes out to be 21,700. And that's going to be the units in that denominator will be GPA times millimeters to the fourth. Young's modulus was given in GPA, all right, and then our Y's are in millimeters. Here on the other side we have megapascals, so that's equal to newtons per millimeter squared. All right, so accounting for the unit conversions that you need, you can solve for the moment and you get 6,078 Newton millimeters. Applying the same stuff to material B, right, which was given a max of 65. All right, that'll be EB times M times YB divided by 21,700. And so, by the way, for the variable distances YA and YB, I'm automatically plugging in the maximum distance from the neutral axis because that's where the stress will be maximum, right? So I'll note that here. So doing the same thing, and I know we're out of time, just bear with me 1 second. Feel free to take off if you need to. This will be on the recording. So here we get a moment of 4,543 Newton millimeters. So since we're looking for the maximum moment that the cross-section can handle, we want to choose the smaller of these two values since material B will govern. All right, any questions? All right, thank you for bearing with me there and sticking in a minute or two extra. Best of luck on the career fair. and I'll see you on Friday.